Section 6.6, normal as approximations to binomial distributions. We talked about binomial distributions before. They were given by the formula probability is equal to the combination of n choose r, p to the r, q to the n minus r. See? Simple stuff. Alright, maybe better if we go ahead and look at that. But luckily we don't need to. One of the reasons why that's not necessarily very useful, especially if we're dealing with a lot of different possibilities, is that we would have to do a lot of calculations. Let's say I wanted to have how many heads there were, or the chance of getting between 50 and 60 heads if I flipped a coin 100 times. I could individually add up each of those probabilities. But the problem is that would require me to do 10 rather complicated calculations and then to add those all together. You can do that in Excel, you can do that in StatLab, or you can do that using an approximation of a normal distribution. So, what do we know? So we have the probabilities of P and Q. We want a sample size such that NP is greater than 5, and NQ is also greater than 5. And then we can deal with it as if it were a normal distribution. So a simple example of that would be if we have a coin that we're flipping. And we do that 10 times. So I've actually already graphed that. That is this right here. Heads. And the probability of those heads. This is the number of flips and the probability of a head. So that's 0.5. This can be approximated by a normal distribution. You can kind of see that it looks like a normal distribution, but not 100% sure. So maybe normal distribution, maybe not, but according to the recommendation, this can be approximated as a normal distribution. Mean will be n times p, or 5, and sigma will be n times p times q, which is 0.5 times the square root of 10, or 1.58. Again, that's for the example that we had before. All right. So what's the difference? Binomial probability distribution is discrete. In other words, we can get 50 heads, we can get 51 heads, 52 heads, we can't get 50.5 heads. Normal distribution is continuous, so that's why it's just a approximation, an approximation. Right. Alright, so for a probability distribution to be a binomial probability distribution, we want to have a fixed number of trials that are independent, flipping heads, rolling a coin, trials that are each classified in 2 categories, success or failure, and trials with the probability or the property that the probability of success remains constant. N, number of fixed trials. Flip a coin 10 times. X, number of specific successful trials. If I flip it, I could have 0 heads, I could have 10 heads. P, probability of success. Q, probability of failure, or 1 minus P. We would expect it to look like this. So this is saying probability of getting a yellow P among 580 Ps. Well, I don't think I've ever seen a yellow P. So chances seem to be pretty small. 0.04. So pretty small there. So let's take a look at what they're saying. We have the following probability histogram. 580, probability is 0.25, so Mendel, who did genetics work, early genetics work, I believe he was a monk as well, expected 25% of his 580 Ps to be yellow, but got 152. So the bell shape suggests that we have a normal distribution to approximate that binomial distribution. So the question is that an unreasonable amount if his hypothesis is correct, his 0.25 is correct? Right? All right. We look at these requirements and we can see that that does satisfy the requirements to do our approximation. Mu should equal n times p, so 0.25 times 680. And then sigma should equal square root of n p q. And we're going to do a normal, we're going to do a correction. We'll go ahead and use the continuity correction so that any number x we have is going to be x minus 0.5 plus 0.5. Right. Check all our requirements and go. So 580 offspring P. 145 of them, 25%, would be yellow. But he actually got 152 yellow peas. Assuming his rate of 25 is correct, find the probability of getting 152 yellow peas or more, given random chance. That is, n equals 580, p equals 0.25, and we want to find the probability we get at least 152. So we'll need to do a z-score, and then we'll also need to make sure that it's 1 minus the probability of that z-score, because we want 152 or more. All right, probability is 0.25. NP is 145. NQ is 435. So greater than 5. Find mu and sigma needed for a normal distribution. Mu is 145, and sigma is going to be 10.4. So 145, 10.4, 1 sigma is going to be about 155, 165 for 2 sigma. Probability of at least 152. So it's going to be 151.5, that's the continuity, up to infinity. We don't care how many yellow, well, up to 680. All right. So we look at our binomial distribution and we look at our area here based on our z-curve. Mu 145. We have a z, which is going to be 151.5 minus 145 divided by 10.4. Look that up on the z-chart, and that'll give us 0.266. So about a 25% chance, or about a quarter of a chance, of getting that number or more. 0.2676. So this is not significantly high. So this does seem like it could follow from Mendelssohn's theory. Right? 25% chance that it's going to be that much higher. If we consider that it's just outside of that range, in other words, that much higher or that much lower, it'd be 25 plus 25, and that's 50%. So that's not particularly bad. All right. And here we're just given some examples of continuity corrections. So if we were to say at least 152, 151.5 plus more than 152, so it doesn't include 152, 152.5. At most 152, so that includes 152, again 152.5. Fewer than 152 does not include 152.5. And exactly 152 would be between 151.5 and 152.5. Alright, so let's use the same information to figure out exactly 152 yellow peas among the 580 offspring. We use the same information we had before and integrate, find the area. If you know calculus, you know why I said integrate, but if not, don't worry about it. Find the area between 151.5 and 152.5 as shown. Pew, pew. Although really, if you're just going to find for an exact one, you could probably just use a binomial approximation for that. and we get an area of 0.0318. So actually a 3.18% chance, which is not unreasonable. So if you were to continuously get 152Ps, that might be a little bit odd, but just one result of 152, again, not particularly different from what you would expect. We can use technology, StatLab, Excel, all that fun stuff. But let's go back. So that's the end of the chapter. I did want to go over this normal distribution again. So I showed you how this looks for 10. So this is the minimum that they allowed. Let's take a quick look at, instead of 10 heads, let's say I had 100. So I can copy this, and I can paste it, and I'll get a total of 100. I have to change this number to 100, because that's how many I have now. And that will give me my new probability. So I'll just go ahead and get a new chart. That might be the easier thing to do. Insert, and let's take a look at this chart. So here is with 100 flips. So we got 0.08, go like that, go like that, and that's going to give us our probability of getting however many heads. And notice that we still have about an 8% chance of getting 50 heads. Now let's say instead of a coin it were a die. All right. And what is my probability of getting a 3 when I roll a die? Well, this is going to be 1 divided by 6. So 1 divided by 6. And with 100 rolls, that would give me this. Notice this is still a normal distribution. And so this still gives me a good approximation. Even if it's heads, even if it's that. And if I wanted to do a graph that just had the lines going together, let's see if I can do that. That simply showed it as a connection of the lines. You can see that it very much looks like a normal distribution. And as we change this probability, it's going to change that distribution, where it is. No longer looks like a normal distribution. It looks exponential. But notice that we can no longer treat it like a normal distribution. N times Q, which is 1 minus P, will actually give us 1. That's no longer greater than 5. So that no longer works to give an approximation as a normal distribution. All right, and that is the end of Chapter 6.